Hi everyone. In today's lesson from section 9-7, we'll be taking a look at circles and finding the lengths of segments, both within the circle and segments that extend beyond the circle. Our first theorem says when two chords intersect inside a circle, the product of the segments of one chord equal the product of the segments of the other chord. So in a general sense, if we take and draw a circle and then draw two chords so that they intersect at some point inside of the circle. And it doesn't matter where the point of intersection is. If we label the endpoints of the two chords A and B for my first chord, and then let's go ahead and use C and D for the endpoints of the second chord. So remember that a chord is a line segment whose endpoints are on the circle. Notice that the two chords are now divided into 4 segments. In this first segment, from point A to the point of intersection, call that R. And the second segment, let's call that S. And line segment CD is also divided into 2 segments, which we can call T and U. So what this theorem actually says is that if we take the product of R times S, it'll be equal to the product of T times U. Simple as that. Alright, so let's put some numbers in and some variables just for a more concrete example. So let's draw a second circle, and again draw 2 chords so that they intersect at some point inside the circle. And again we can call the first chord A, B, and the second chord C, D. So this time around we're going to be given some information about the lengths of those segments. So this first segment is going to be labeled with 2x, and the other half of, other part, not half, but other part of that segment is going to be labeled with x. And our chord CD is divided into 2 segments that are 10 units long and 4 units long respectively. So according to our theorem, we can take 2x times x, and we'll set it equal to 10 times 4. So we've got 2x squared is equal to 40, and then take and divide by 2, and we end up with x squared is equal to 20, and take the square root, and when we simplify that, we end up with 2 square root of 5. Final answer for x. Just make sure you go back and look at the directions in tonight's homework to make sure that there aren't any other segment lengths that you need to find. Like you might be asked to go back and find the length of line segment AB, for example. Okay, in our second theorem for today, in theorem 9-12, it says when 2 secants are drawn to a circle from an external point, the product of one secant segment and its external segment equals the product of the other secant segment and its external segment. Okay, so recall that a secant is a line or a line segment going through a circle, and it might continue past the circle or it might have an endpoint like right on the circle here. So if we draw a second secant, and they're going to meet at this external point, which we'll just call point P. Okay, so in our first secant, I'm going to call this point of intersection A, this intersection B, so we can call that secant AB, and the second secant, we'll just refer to it as CD. Okay, so the theorem again says the product of one secant segment, that's referring to the whole secant from A to P, and we're just going to give that the variable R to represent it. So the product of that whole secant segment and its external segment, the external segment for that secant would be this piece right here. So let's say that that piece has a length of S. So we're going to take R times S, so whole secant segment times external segment is equal to the product of the other secant segment, so that's this whole secant, which we'll call T, times its external segment. So whole secant times the external piece. So let's call that external piece right here u. Okay, so we take r times s and set it equal to t times u. So whole secant times part equals whole times part. So let's throw some numbers in there. So we'll draw a similar picture. Again, two secants meeting at a point outside the circle. So I'll just call that point P. And this will be secant A, B. And this is secant C, D. Alright, and if we take a look here, let's call this segment 8 and this segment 4. And this segment has a length of x and this segment has a length of 6. So let me just clean this up a little bit because we want this segment to have a length of 4. It looked like x. Now recall that the theorem says that we have to take the whole secant. So the first thing you need to do is find the length of the full secant segment from point A all the way to P. So just use segment addition to figure out that that's 12. Come down here and do the same thing with this whole secant. We have to represent it by x plus 6. Okay, so in applying the theorem, we're going to take the whole secant length, 12, times the external segment, 4. You're going to set it equal to this whole secant, x plus 6, times the external piece, which is 6. Okay, so we're going to have 12 times 4, which is 48, equal to 6x plus 36 when you distribute. So you end up with 12 is equal to 6x, and that will give us x is equal to 2. Again, go back in and check your work by plugging 2 in for x and just making sure that it works in the theorem. Okay, our final theorem for today, 9-13, states when a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment and its external segment is equal to the square of the tangent segment. Okay, so if we start off with a circle, and it says we have a secant segment, which will be my red line segment here, and we have a tangent segment. I'm going to do that one in blue. And that a tangent segment touches the circle in exactly one point. Okay, so the red is the secant, touches the circle in one point. The blue, secant touches the circle in 2 points. The blue is our tangent. It touches the circle in exactly 1 point. So for the naming of our secant, we'll say it's line AB. The secant and the tangent will meet at point P. Okay, so applying the theorem, it says when a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment, that means the whole length of the secant segment, which we'll represent by r, and its external segment, which we'll represent by s, that product, r times s, so whole segment of your secant times this little external piece, it's equal to the square of the tangent segment, which we'll represent with lowercase t. So r times s is equal to t squared. Okay, so in a practical sense, with some numbers thrown in there, we have a circle, we have a secant intersecting the circle at 2 points, and we have a tangent. Kind of missed the mark there, but imagine we've got that point of tangency. Okay, so imagine that, and this is in no way drawn to scale because I'm drawing it pretty quickly. We have the length of this portion of the secant is 18, and the length of this external piece is 6. And the length of our tangent segment is x units. Okay, so applying the theorem, remember that we have to take the product of the whole secant segment. So we want to do whole secant times external segment equals the tangent squared, the tangent segment squared. This is our tangent over here. Okay, and again, this whole distance is our secant. So take a second and find that whole length just by adding those two together. We've got 24. So we're going to do 24, the length of the whole secant, times 6, the length of the external segment, and that's equal to our tangent squared. So it'll be equal to x squared. Well, 24 times 6, luckily enough, is 144, equals x squared. And when you take the square root, you just come up with x equals 12. Okay, good luck on homework number 7. Please don't hesitate to send me an email or stop by my room tomorrow, like before or after school, if you need some extra help.